Hi dear students, today we'll discuss about heterocyclic compounds. As you all know, this is one of the very important chapter in organic chemistry part of the BSc 5th Sem chemistry. So it carries about 8 to 10 marks in your exam also. So that's why it's one of the very important chapters in your syllabus. So it is there in all university syllabus for BSc final year students. So we'll discuss it right now. So, as you all see, heterocyclic compounds. The name heterocyclic includes two words. The first word is hetero, which is a Greek word from heteros, which means different, which means different. And the another word, cyclic, that means ring structures. That means ring structures. Usually in organic chemistry, we see the rings like benzene ring, where we can see that all the ring atoms here are the carbon atoms. So in this case, if one of the carbon atom in the ring, if it is replaced by any other element other than the carbon, for example, I am going to replace this carbon with nitrogen. So such compounds, this compound now become a heterocyclic compound. So I have just replaced a carbon in benzene, and with the nitrogen, that becomes an heterocyclic compound. For example, this is benzene and its name is pyridine. It is one of the very important heterocyclic compound. As we have seen, it is used as a organic solvent. So now using these terms, we can now define the heterocyclic compounds. So if I write the definition of heterocyclic compound, please see here. The cyclic organic compounds where one or more carbon atoms in the ring, that you should remember, not outside the ring, in the ring, has been replaced by heteroatom, replaced by a heteroatom. So such compounds are known as heterocyclic compound, are known as heterocyclic compounds. This is the definition of heterocyclic compounds. The definition says the cyclic organic compounds where one or more carbon atoms are replaced by the heteroatoms. So here you can see heteroatom is the nitrogen. The most common heteroatoms we find in heterocyclic compounds are nitrogen, oxygen, sulfur. And in few compounds we can also see phosphorus, boron, silicon, etc. So these three are very important. The heterocyclic compounds containing nitrogen, oxygen, sulfur. We are going to discuss those compounds in this chapter. And to discuss before the heterocyclic compounds, we must know the scope of the compound. Why should we study this? because these are involved in our daily life, even in our life. Okay, so if you see its biological role, actually its chemical role is so much high now, because these are heavily used in chemotherapeutic agents, dyes, and also polymers, copolymer. They are used as copolymers. But in biologically also they have been naturally involved in our system. So for example, it is also present in DNA, all adenine, guanine, thymine, cytosine, the uracil, those all are containing heterocyclic compounds, or nitrogenous bases. In DNA, also in RNA, in heme, hemoglobin, heme, and also in chlorophyll in plants. Okay, these all have been in the very important chapter that we are going to study in the next next chapter, that is our alkaloids. That is also usually there for final year students. We can see there the heterocyclic compounds. So that's why we should study this compound in detail. If you see some synthetic polymer, synthetic heterocyclic compounds, the synthetic heterocyclic compounds are also used as chemotherapeutic agents, that is the commonly known as drugs, and copolymers, and also dyes, where we can see the synthetic heterocyclic compounds are also being used. These are naturally heterocyclic compounds found in this RNA, DNA, and etc. Now we have the application of these heterocyclic compounds even in these industrial things. In classification of heterocyclic compounds, there are two methods. We can classify them heterocyclic compounds by the size of the ring, and also their nature, whether they are aromatic or non-aromatic. So first, very important one is, we have to see the classification based on size of the ring. Size of the ring. It means how many atoms or elements present in the ring. Size of the atoms. Size of the rings. Okay. Here, if I consider this is first method, one. The first one is minimum we should have three elements to form a ring. That's why first one is three-membered heterocyclic ring. Three-membered heterocyclic compounds. HCC, I am writing it in short form abbreviation. Three-membered heterocyclic ring. You see, in three-member heterocyclic rings, the ring has to be made up of three atoms. So at least one must be the our heteroatom. For example, yes, this one. This one is known as oxirane. Oxirane. This is a oxygen heterocyclic compound. And if you have nitrogen, this is aziridine. Aziridine. The same way, we can also have sulfur. This is thiorane. Thyrane. Thyrane, not thiorane, thyrane. Okay. So these are three-membered heterocyclic compounds. The same second one, that is four-membered heterocyclic compounds. Four-membered heterocyclic compounds. So here the heterocyclic ring is made up of four atoms, the one of which, at least one of which, should be the heteroatoms. For example, the nitrogen heterocyclic compound. This is acetidine. Acetidine. The same oxygen. This one is oxetane. Oxetane. Same way for sulfur. Thietane. Thietane. These are four-membered heterocyclic compounds. The third one is five-membered heterocyclic compounds. So here now, for example, from now onwards, we can see the aromatic heterocyclic compounds also. These all are aliphatic or alicyclic heterocyclic compounds. So here, this is one of the very important heterocyclic compound. This is known as pyrrole. Pyrrole. And its aliphatic version, that is, this one is pyrrolidine. Pyrrolidine. And oxygen, this one is known as furan. This is also very important compound we are discussing in this chapter. And its aliphatic version, oxolane. Oxolane. For sulfur, this one is known as thiophene. Thiophene. And its aliphatic version, thiolane. Thiolane. So most of these aromatic heterocyclic compounds are very important because they are more stable. So that's why we'll study in further details. The fourth class is six-membered heterocyclic compounds. Six-membered heterocyclic compounds. Here the heterocyclic ring is made up of six atoms. At least one should be the heteroatom. For example, the important compound we are discussing in this chapter is six-membered. Okay, this one. This is known as pyridine. Pyridine. And its aliphatic version, piperidine or piperidine. Piperidine or piperidine. And one more important one, that is oxygen. Not we are discussing in this chapter, but this is also we are seen in glucose structure. That's why it is pyran. Pyran. So this pyranose ring we see glucopyranose, the Howard structure of glucose. In this pyran we see in fructofuranose, that is in the furan Howard, that is in the fructose Howard structure. So these are also involved in biomolecules. And this oxolane is also actually known as THF, tetrahydrofuran, which is also one of the very good solvent, especially in spectroscopy. We use that NMR, we use that solvent. So this pyridine is also solvent. So and THF, and most of these compounds have definitely industrial applications. So these are the primary, and you can also classify them as six-membered, seven-membered. So this six-membered, seven-membered, eight-membered. So it goes on. But especially this five-membered and six-membered have lot of applications, and these are very important heterocyclic compounds. So that's why we discuss these compounds in detail in this chapter. Especially these aromatic heterocyclic compounds like pyrrole, furan, thiophene, piperidine. These four compounds we are discussing in this chapter in details. And the second, so this is the classification based on the size of the ring: 3-membered, 4-membered, 5-membered, 6-membered. You can also 7, 8, it doesn't worry. But in your exams, usually these things are very important, those may ask. And there is one special heterocyclic compound in based on this size of the ring, that is fused heterocyclic compounds. Fused heterocyclic compounds, it is also known as condensed heterocyclic compound. As name itself tells us that heterocyclic compound is fused with other rings. So here this heterocyclic compound is fused with other ring, fused with other rings. For example, you can see here this pyrrole is going to be fused with benzene, and this pyridine is also going to be fused with benzene. Let's see that. For example, benzene, to which this pyrrole has been fused. This compound is known as indole, and here benzene, to which 6-member. Okay. So this one pyridine has been fused. This one is known as quinoline. Quinoline. So this is a special class in heterocyclic compound that has been asked many times. What are fused or condensed heterocyclic compound? Give an example. So this 3-membered, 4-membered, 5-membered, 6-membered fused heterocyclic compound. You can also write 7-membered if you, but it's okay. Usually 5-membered and 6-members are very important, because especially those aromatic ones, and those are also very important. And in this chapter we are going to study in detail about pyrrole, furan, thiophene and pyridine. And the second method for the classification of heterocyclic compounds, that is based on whether they are aromatic or not, non-aromatic. Based on the structure itself, you can see whether they are aromatic or aliphatic. So here it is aliphatic or alicyclic. It is also aliphatic. It is also aliphatic. Aliphatic, 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 aliphatic. These all are aliphatic. So these we can classify as aliphatic heterocyclic compounds. And these pyrrole, furan, thiophene, pyridine, pyran, these all are aromatic heterocyclic compounds. We can just write based on their nature, we can classify them. So this is about the classification of heterocyclic compounds. Thank you, and I hope you all got it. And please like the video and share with your friends and subscribe to my channel. Thank you. Dear students, now we'll discuss molecular orbital structure of pyrrole. This is one of the very important question for 5 marks. Please note it. And you have the molecular orbital structure of pyrrole, thiophene, furan, and also for the pyridine. One of which will definitely come in your exam for 5 marks or 4 marks. So that's why please have attention completely and please listen. So you already know seen the structure of pyrrole, that is, this is the structure of pyrrole, a 5-membered heterocyclic ring. In the ring, if you see, there are carbon and nitrogen. So the carbon and nitrogen atoms are there in the ring, and both of them are sp2 hybridized. Both of them are sp2 hybridized in the pyrrole. So if you see for carbon atom, the atomic number of carbon is 6, and if you see its electronic configuration in ground state is 1s2, 2s2, 2p2, and in the excited state the electronic configuration of carbon in excited state, that is 1s2, this is 2s and 2p orbitals. So one of the 2s electron will shift to the higher energy orbital, that is 2p. So here it becomes 2s1 and 2p3. So if I put the box for these electrons, you know inner orbitals do not involve in the hybridization. So that's why I am putting the orbital. This is 2s orbital and these three are 2p orbitals. 2p orbitals. You know in case of 2p there is a px, py and also 2pz. If you see here, in case of 2s, there is one electron. In 2p3, 1 electron. And for nitrogen, atomic number is 7. If you see the electronic configuration in ground state, that is 1s2, 2s2, 2p3. The same electronic configuration in excited state is 1s2, 2s, 2p. Here also in excited state, one of the s orbital, 2s orbital shift to the 2p orbital. So it is 2s1, 2p4. And if you put the box for 2s and 2p orbitals, so this is for 2s orbital, and I'm going to put the box for box orbital structure for 2p. Here we have 2p. So you already know this is one is the px, 2px, 2py and 2pz. 2. Okay. So here in 2s there is one electron, in 2p 1. Actually, according to Hund's rule, we have to pair up this to first one orbital, but all of actually the degenerated orbital they have same energy. But in excited state, the electron is always present in as highest energy carrying orbital. So here we have these structures. So here these orbitals, which one? These 2px and 2py or any two of the 2p orbitals and 2s orbital involved in the hybridization. So these all three will involve in sp2 hybridization. So now then they will become sp2 hybrid orbitals. And here also the same thing happens. One of the 2s and 2p orbitals. So these two will become sp2 hybrid orbitals. And in case of carbon and also nitrogen, there is one orbital which is not undergoing hybridization, that is 2pz here. So this is an unhybridized p orbital, and here it is also unhybridized p orbital. Okay. And in the case of carbon, there is one unhybridized p orbital. In case of nitrogen, there is also one unhybridized p orbital. It containing a single electron, an unpaired electron. With unpaired electron in case of carbon, and here in case of nitrogen, it is containing pair of electrons, or electron pair of electrons. So unhybridized p orbital with pair of electrons. So we should have this summary with us. So for carbon, we have how many? 3 sp2 hybrid orbitals, each containing unpaired electron. Those only will be involving in the sigma bond formation further, and one unhybridized p orbital. I hope you see it till here, with unpaired electron, and for nitrogen atom there is also 3 sp2 hybrid orbitals and one unhybridized p orbital here with pair of electrons. This is we got from their electronic status, and now we'll see the how they are forming bonds, and we can write the molecular orbital structures. This you may not need to write in the exam, because we should know how these all come. This is what you need to write. So from here, so now I will see the formation of first sigma bond. You all know in case of chemical bonding, so first formation of sigma bond takes place, then pi bond will continue. Formation of sigma bonds in pyrrole. Okay, there are 4 carbon atoms, one carbon, second carbon, another carbon, and one nitrogen. And you all know each of these carbon are undergoing have undergone hybridization, which is that is sp2 hybridization. So you must know when they undergo sp2 hybridization, their geometry will be trigonal planar. Trigonal planar. So please note down this geometry. So and each carbon and each nitrogen have undergone sp2 hybridizations. Hence they have occupied the trigonal planar geometry. So for example, I am not writing small lobe, I am writing only larger lobe. This all carbons and all nitrogen will have the same geometry in this case. So these 3 are the hybridized sp2 hybridized orbitals of carbon. For the same nitrogen also we have the same thing. So geometry you can see these all are having sp2 hybridization. So one of the sp2 hybrid orbital of carbon will overlap with the another sp2 hybrid orbital of carbon. So this and each of them are containing unpaired electron. You can see the structure here. So here both of them will get paired up and forming a carbon-carbon sigma bond. So this overlapping is sp2 overlapping. This happens in all the cases. See here also this carbon, one of the sp2 hybrid orbital overlap with this carbon. So this is also sp2 overlapping. I'm just writing sp2. Here one orbital is there that is containing unpaired electron, and here also it is overlapping with nitrogen sp2, the sp2 hybrid orbital of nitrogen. So this is also sp2 overlapping, because nitrogen is also sp2 hybridized orbital containing sp2 hybridized orbital. You can see this is the overlapping, and in this case here also the carbon and nitrogen forming sigma bond by the overlapping, that is sp2 overlapping. Here also the same carbon sp2 overlapping, and each of the carbon and also nitrogen still containing an sp2 hybridized orbital with nitrogen, with with unpaired electron. So you know the formula, molecular formula of nitrogen, that is molecular formula of nitrogen is C4H5En. We have just discussed about the carbon and nitrogen. There is also 5 hydrogen atoms. So these, the remaining sp2 hybrid orbitals of each carbon and this nitrogen will overlap with the s orbital of the hydrogen. So here this is the overlapping. This overlapping is sp2 of carbon and s of hydrogen. This is sp2 s overlapping, forming CH carbon bond, CH sigma bond. Here also the same thing. So you know the geometry of hydrogen orbital, that is only one orbital, 1s1. So the s orbital shape is spherical. So here also the nitrogen and hydrogen forming the bond, that is single sigma bond, by the sp2 s overlapping. Here also the same carbon, remaining carbon also same thing happens. Here also the same thing happens. So what we get, this is the molecular orbital structure for the formation of sigma bond for pyrrole. So you have to also write the inference of this sigma bond formation at the end. So here you can see there is 3 types of bond, that is one is CC bond, another one is CN bond, and another one is 4 types, NH bond and CH bonds. So these all are you have to write at the end. So first you should write at the end, that is carbon carbon sigma bond and carbon nitrogen sigma bonds. These both are formed by sp2 overlapping and carbon hydrogen sigma bond and nitrogen hydrogen sigma bond. These are formed by sp2 s overlapping. As you all know, hybridized orbital form only the sigma bonds, otherwise they will just be as a lone pairs. So this is the molecular orbital structure for the formation of sigma bond to the pyrrole. Now after the formation of sigma bond, we will now move to the formation of pi bonds. We will see now the formation of pi bonds. Yes, now we will see the formation of pi bonds. Yes, we already got the molecular orbital structure of this for sigma bonds. That only I am writing, but I am forming its bonds here. This is equivalent structure to the carbon carbon sigma bond, carbon carbon sigma bond, the carbon nitrogen sigma bond, carbon carbon sigma bond, carbon nitrogen sigma bond, and each of them are having a sigma bond with hydrogens. So this is the equivalent structure. So that only I am writing here. Yeah. This is the structure we get after forming the sigma bonds, and you know each of the carbon and also the nitrogen still have a an unhybridized p orbital. So let me draw that. You know the geometry of p orbital is dumbbell. So this unhybridized p orbital is present perpendicular to the plane of the sigma bond. So you know if they are in the plane, then they form a axial overlapping, that is leading to the formation of sigma bond. But these all unhybridized p orbitals are present perpendicular to the plane of the sigma bonds. So that's why they always form the pi bonds. So in case of carbon, each of the carbon orbitals having a unpaired electron, and nitrogen is having a pair of electrons. These all will show the now sideways overlapping or lateral overlapping, upper lobe, lower lobe. Here also the upper lobe, lower lobe, upper lobe, lower lobe, upper lobe, lower lobe, upper lobe, lower lobe. So these will show the axial or sideways overlapping. This is actually the forming this structure. This is equivalent to the structure, that is carbon sigma bonds are already there. Yeah, hydrogen sigma bonds. And now they are forming a pi cloud actually. So this is like a cloud over the plane of the sigma bond and also the below the sigma bond, that is forming a sigma pi bonds. So now it is forming a cloud like this, pi cloud. Or there are totally 6 electrons are involved in the pi cloud. Here 2 electrons, third, fourth and fifth and sixth here. So this is also this equivalent structure, or equally this is also equivalent to the structure of pyrrole. If we do not mention the structure of nitrogen and carbon atoms and also hydrogen atoms, you can write like this also. Otherwise, or if you want to mention the pi bonds, when you mention the pi bonds, there are only 2 pi bonds and these lone pair also involving pi cloud. So that's why we can write like this. I have written. Okay. Yeah. This is the structure we get from this molecular orbital structure. That is the pyrrole structure. So this is the molecular orbital structure for sigma bond formation, and this is for the pi bond formation. You can write both of them in the exam. That is very good. Okay. Yeah. This is about the molecular orbital structures of pyrrole. Please note these: CC sigma bonds, CN sigma bonds, NH sigma bond and CH sigma bonds are formed by sp2 overlapping and sps overlapping respectively, and these are the unhybridized p orbitals of carbon and nitrogen atoms will shows a sideways overlapping or lateral overlapping, that is forming a pi bond. So these both are the molecular orbital structures of pyrrole. And we also have a very important small topic, that is the aromaticity of pyrrole atom. So we all know that pyrrole is an aromatic compound. So that's why we should give a proof, or we know the criteria of aromaticity. So whether it fits or fulfill all the criteria of aromaticity or not. If it definitely fills it, I know it is definitely fills and it is aromatic. So let us see that how it fulfill the criteria for aromaticity. So if you write the aromaticity, so you also, if you see the PYQs of your exams, most of the times for 2 marks also, that aromaticity of pyrrole, thiophene or furan or even pyridine also has been given. So you should know. So the aromaticity, you know, there are 4 criteria. The first criteria is the compound must be cyclic, planar, cyclic and planar. You know, the pyrrole is having sp2 hybridization, so hence it has a structure of trigonal planar. So all sp2 hybridized orbitals are having actually gives a planar structures, hence it fulfills the first criteria. So you should here write completely like pyrrole is a cyclic planar structure. Okay. The second one, yeah, it undergoes conjugation. It shows the conjugation or resonance conjugation and resonance due to delocalization of pi electrons. Pi electrons. So in the structure you can see there are two pi bonds, means 4 pi electrons, and also lone pair of electrons. All these 6 are showing actually delocalized, they delocalize and forming a resonance structures. We will see the resonance structures and reactivity in the next topic. So this the third point is it should obey Huckel's 4n plus 2 pi electron rule. So you know it obeys the 4n plus 2 pi electron rule because here also n equals to number of ring is 1. So I'll write here n equals to 1. 4 into 1 plus 2. This is equals to 6 pi electrons. 6 pi electrons. In the structure, these 2 pi bonds gives 4 pi electrons, and this lone pair is also involving in delocalization, as just now I said. So that's why totally 6 pi electrons. Totally 6 pi electrons are there in the pyrrole. Hence it also fulfills the third criteria also. So all the first, second and third criteria has been fulfilled, and the fourth is, that is the presence of at least one hydrogen, because we also know if it has to be an aromatic, it should show its properties like reactivity, that is electrophilic substitution. So it has how many hydrogens are there? So totally there are 5 hydrogens are there. In the formula itself we had 5 hydrogens. So there are, yeah, you can write like this. There are 5 hydrogen atoms present in the pyrrole compound. Hence they undergoes electrophilic substitution. Electrophilic substitution. So this also obeys or fulfills the fourth criteria. The fourth criteria, please remember, the compound must be cyclic and planar. The first criteria. Second criteria, it should show delocalization of pi electron, which is actually leading to the resonance in the structure, or it shows the conjugation. So that is also we can see in the case of pyrrole. We can see in the next class when we come to the reactivity. And it also obeys the Huckel's rule, Huckel's 4n plus 2 pi electron rule. You see it has a 4 pi electrons and the lone pair of electrons, all 6 electrons involved in the resonance structures, and they are actually responsible for the resonance. You know the compounds containing 2, 6, 10, 14, 18 pi electrons are aromatic in nature. So it has a 6 pi electrons. So hence it is also aromatic in nature. In the fourth rule, it has a 5 hydrogens. At least we need 1 hydrogen for electrophilic substitution reaction, but it has 5 hydrogen atoms for electrolytic substitution reaction, and it is also showing very easily the electrophilic substitution reaction because it has 5 hydrogen atoms. Hence all these 4 criteria has been fulfilled. Hence we can now declare that therefore the pyrrole is aromatic in nature. Pyrrole is aromatic. So this is very important. Sometimes they ask only the molecular orbital structure, and otherwise they will also ask write the molecular orbital structure of pyrrole and mention its aromaticity. Then you have to need to write all these things. Please note down This is one of the very important topic in these heterocyclic compounds. And thanks for watching the video. Please like the video, share with your friends, please subscribe, and also hit the bell icon to get the updates of the next videos that will be uploading from me. Thank you. Bye me. Hi dear students. Today now we'll discuss the molecular orbital structure of furan. This is also one of the very important topic in your exam. This is also for 4 marks or 5 marks, and it is usually there for the final year BSc students in chemistry. So you know, furan is an heterocyclic compound as we discussed in the last classes. So furan, its molecular formula, furan is C4H4O. And if you see the structure, this is the structure of furan. It is an heterocyclic compound containing and one oxygen as a heteroatom. So here we have carbon and oxygen. Both carbon and oxygen are sp2 hybridized. Both of them are sp2 hybridized. Yeah. For carbon atom, the atomic number of carbon is 6. Its electronic configuration in ground state is 1s2, 2s2, 2p2. The same electronic configuration in excited state for carbon atom, 1s2. This is the valence orbital, second orbit. So here 2s, 2p. In excited state, one of the 2s orbital will shift to the 2p orbital. So it will be 2s1, 2p3. If I put the box of orbitals for these orbitals, and you know inner orbitals like 1s orbital does not involve in hybridization, hence I am putting box for 2s and 2p orbitals. This is for 2s, and in case of p orbital there are 3 subatomic orbitals, that is in case of 2p, one is px, py, pz, that is 2px, 2py and 2pz. Yeah, here in case of 2s there is one electron, in 2px there is one electron, 2p1 1, there are 3 electrons. Okay, as it is undergoing sp2 hybridization, one 2s orbital and 2p orbitals will be undergoing hybridization, that is giving us 3 sp2 hybrid orbitals, and the remaining one is an unhybridized p orbital. P unhybridized p orbital. Okay, and for oxygen atom, the atomic number of oxygen is 8, and if you write the electronic configuration in ground state, that is 1s2, 2s2, 2p4, 2p4, and same electronic configuration of oxygen in excited state is 1s2, 2s, 2p. Here the same thing happens, 2s1, 2p5, 2p5. Yeah, if I put the box for these orbitals 2s and 2p, 2s, 2p. Among 2p there is 2px, 2py, 2pz. In case of 2s, one electron is there here, 1 1 1 in excited state. It is against Hund's rule, it does not follow the Hund's rule. That's why in the last two orbitals we have pair of electrons. And if you see here also, it is also undergoing sp2 hybridization, hence 2s orbital and 2p orbitals, 2s are one orbital and 2p orbitals will undergoing hybridizations. So here these are become 3 sp2 hybrid orbitals, and there is also one unhybridized p orbital. Yeah, unhybridized p orbital. If you write this electronic status, here I will writing for carbon atom, it is actually showing sp2 hybridization, and we have here, yes, 3 sp2 hybrid orbitals with unpaired electron, with an unpaired electron in each, and there is one unhybridized p orbital which is containing, that is also with a unpaired electron, with an unpaired electron. Yes, for carbon atom, that is also sp2 hybridized. Here you can see one of the 3 sp2 hybrid orbitals, sp2 hybrid orbital containing pair of electron, and the remaining two are unpaired. So 3 sp2 hybrid orbitals, among which 2 orbitals, 2 sp2 hybrid orbitals with an unpaired electron, and one of the sp2 hybrid orbital is containing a pair of electron, with pair of electron. This is the electronic system, electronic status of the carbon and oxygen in the furan ring. Now we will discuss the bond formation, that is, we are going to write the molecular orbital structures. First we will write the molecular orbital structure for the formation of sigma bond, and later we will write the molecular orbital structure for formation of pi bonds for the furan atom. Now we will write formation of sigma bonds. Sigma bonds. In the structure you can see there is a sigma bond between carbon and carbons, and also carbon and oxygen, and each carbon is linked to the hydrogen atom. There are 3 types of sigma bonds, that is carbon-carbon sigma bond, carbon-oxygen sigma bond, and carbon-hydrogen sigma bond. Let us see all that. See formation of sigma bonds. You know, as both carbon and oxygen are sp2 hybridized, so then the sp2 hybrid, if it is sp2 hybridized, then the geometry will be trigonal planar. The geometry is trigonal planar. You know the geometries earlier in hybridization classes. So now let me write the sigma bond formation. So there are 4 carbon atoms. So 1 carbon, 2nd carbon, 3rd carbon, 4th carbon, and there is an oxygen atom. Yeah. And each of the carbon and oxygen are sp2 hybridized, hence they will get the trigonal planar geometry. This is the geometrical shape of the orbitals for both carbon and oxygen. So here what happens? Each of the sp2 hybridized orbital of carbon containing unpaired electron. So each of them are containing a single electron. And this electron or this orbital, especially orbital, overlap with the sp2 hybrid orbital of the another carbon. So it is get paired up and forming a Cc sigma bond. Cc sigma bond. You can see this overlapping is, this is an sp2 hybrid orbital and this is also sp2 hybrid orbital of the this carbon. So this is the sp2 overlapping, that is leading to the formation of carbon carbon sigma bond. The same thing here also, this carbon is still having one more orbital with an unpaired electron, and that overlaps with another hybrid orbital, sp2 hybrid orbital of another carbon atom, and forming a, this is also sp2 overlapping, forming a carbon carbon sigma bond. And here also carbon, one of the, you can see in oxygen there is two sp2 hybrid orbitals with unpaired electron. Yeah, these both are unpaired, and another one is pair of electron. Yeah. So the sp2 hybrid orbital containing unpaired electron will overlap with the sp2 hybrid orbital of the carbon with the unpaired electron. So this overlapping is also sp2 overlapping and forming a carbon oxygen sigma bond, CO sigma bond. The same thing here also, carbon carbon sigma bond, and here carbon oxygen sigma bond. So here it is a carbon, this is also sp2 overlapping, then this one is also sp2 overlapping. This is how we can form the carbon carbon sigma bonds and carbon oxygen sigma bonds. And still each carbon containing an hybrid orbital, sp2 orbital with a lone pair of electrons. You can see all the four carbons. So this will overlap with the s orbital of the hydrogen atom, forming CH sigma bond. This overlapping is, one of the orbital is sp2 hybrid orbital and another one is s orbital of the hydrogen. This overlapping is sp2 s overlapping. So please remember, sp2 s overlapping will lead to the formation of, result in the formation of carbon hydrogen sigma bond. Here also the same thing happens. So this hydrogen s orbital and sp2 hybrid orbital of carbon atom will overlap, forming CH sigma bond. Here also the same thing happens, CH sigma bond. The oxygen is free. Here one more carbon. Yeah, actually this is the molecular orbital structure of furan for the formation of sigma bonds. And if you see its inferences, you hear the carbon sigma bond and carbon oxygen sigma bond, carbon sigma bond, carbon oxygen sigma bond. These both are formed by sp2 overlapping, sp2 overlapping, and the remaining carbon bond is carbon hydrogen bond. So carbon hydrogen sigma bond, this one is formed by sp2 hybrid orbital of carbon and hybrid s orbital of hydrogen, that is sp2s overlapping. This is very important. This is the molecular orbital structure of furan for the formation of sigma bond. After this, I hope you see, this is very important. You should mention, and you should mention these also, and you do not need to write these things electronic status in the exam, because they are only asked for the, they definitely ask only for the molecular orbital structures. If you write this one also, no problem, but this much you at least you need to mention these things and these things. Even if you write like this point wise also, you will definitely get a full marks, because you should mention what is happening perfectly. Okay, the electronic system electronic status of carbon and hydrogens. Sorry, this is for oxygen atom. Okay, and here the formation of sigma bond. Please remember, carbon carbon sigma bond and carbon oxygen sigma bond are formed by sp2 overlapping, and carbon hydrogen sigma bond is formed by sp2s overlapping. After this, we will now write the molecular orbital structure for the formation of pi bonds. Yeah, and please remember, this is also very important. Still, the oxygen is containing a lone pair of electron in the same plane of the sigma bond. So this is a non-bonding pair of electrons. They do not involving in any kind of bond formation in the furan for this compound. So please remember, these are a non-bonding pair of electrons of oxygen in the furan. They do not have any functional aspects in the formation of the structure. Okay, so they will have some, definitely there are some reactive properties that we'll discuss in the next class. So please remember, the oxygen is still containing a lone pair of electron which is not involved in the bond formation. Hence it is a non-bonding pair of electrons or lone pair of electrons of oxygen. So please remember, each carbon and oxygen are sp2 hybridized, and in carbon, all the sp2 hybrid orbitals are containing unpaired electrons, and there is one unhybridized p orbital with a single electron or unpaired electron. For oxygen, among 3 sp2 hybrid orbitals, 2 sp2 hybrid orbitals are forming are with an unpaired electron. Those are forming sigma bonds. There is still one more hybrid orbital with a pair of electron that do not form any kind of bond. That is a non-bonding pair of electron. But still we have one more p orbital, that also I should mention here. I'll write here now. One unhybridized p orbital is also present in oxygen with, see, that is also with pair of electron, I think I forgot to write here when I was talking about this. Please, you mention it. Okay, you can now take the screenshot of this one because that is very important. Even if you write this much also, you will definitely get a full marks. And after the formation of sigma bond, now we will see the formation of pi bonds. Students, formation of pi bonds. Okay, so you know, always pi bonds are formed after the formation of the sigma bonds. So when sigma bond is formed, if you write the bonding structure, this is equivalent to this structure. There is a carbon carbon sigma bond. Yeah, these all are sigma bonds, and also it has bond with hydrogen, 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 and this still oxygen is carrying a pair of electron in one of the sp2 hybrid orbital. So I write that structure and I'll show the formation of pi bonds. So after the formation of the sigma bond, we have this structure. Yeah. Yeah, we have already seen that in carbon and both in oxygen, there is one unhybridized p orbital with unpaired electron, and one unhybridized p orbital with pair of electrons. These unhybridized orbital forming pi bonds over here. So each carbon shape of the p orbital is dumbbell C, and all these unhybridized p orbitals are perpendicular to the plane of the sigma bonds. Okay, perpendicular to the plane of the sigma bonds, and each of the carbon unhybridized p orbital are having a single electron, unpaired electron. So just for our convenience, I can write the opposite spins. Yeah. And in case of oxygen, there is a pair of electron. The unhybridized p orbital of oxygen is containing a pair of electrons. These orbitals are now showing an sideways overlapping or lateral overlapping. The upper lobe overlaps laterally or sideways. Here also upper lobe, lower lobe, upper lobe, lower lobe. Here also this upper lobe, lower lobe. Yes. This is the final molecular orbital structure of furan. Now you can see here the sigma bonds are already formed, and now these sideways overlapping are forming the pi bonds, the complete bonds. Here now we can see in this structure. This is the final structure of molecular orbital structure of furan. So you know the sigma bonds are always formed by head to head overlapping or in a axial overlapping, and pi bonds are formed by sideways overlapping. So this is the final structure. You know here carbon are all unhybridized p orbitals and oxygen unhybridized p orbital. Totally each carbon 4 electrons, and this one for oxygen, that is also forming giving a pair of electron. The another pair is non-bonding, that is as it is. You can see here that does not forming any kind of bond. So in case of there are two orbitals in case of oxygen. One is hybridized, that is not forming any bond with a pair of electron, and there is also one unhybridized pair of orbital, p orbital, with a pair of electron that is forming a pi bond. So though here you can see 1 1 1 1 2. So each carbon is giving 1 electron and oxygen is giving 2 electrons. So totally there are 6 delocalizing electrons. 6 delocalizing electrons. So here you can see this is the molecular orbital structure. This is equivalent to here. You can see now carbon, oxygen. So our oxygen, there is a one lone pair. One of the pair involved in the bond formation, and one pair is not involved in the bond formation. And here there is a pi bond. Pi bond is forming, and each carbon is having a sigma bond with hydrogens. This is equal to this structure. Or you can write like this also. If you show the electron cloud, pi electron cloud, we can now completely mention all oxygen, and so like this you can write. Here I have shown the lone pair of electron that those involved, sorry, the pair of electron involved in the bond formation. Here I am not showing because I have shown the pi cloud. The pi cloud is containing these 2 electrons. The one pair is a lone pair, is non-bonding pair. That's why I am writing at the outside the ring. Okay, this is about the molecular orbital structure of furan. Students, usually the questions are framed like write the molecular orbital structure of furan and mention aromaticity. Really the questions you asked along with the aromaticity. So that's why we'll see the aromaticity of furan now. To compare any compound, if it has to be aromatic, then it has to fulfill 4 criteria of aromaticity. So let us see one by one. The first criteria is the compound must be cyclic and planar. Cyclic and planar. In the case of furan, you know it is a ring structure. Ring means cyclic, so it fulfills the first one, and it is a planar in geometry. So as you seen in the molecular structure where it is carbon and hydrogen, carbon and oxygen, all of them are undergone sp2 hybridized. sp2 hybridized means trigonal planar geometry, so it is also planar in nature. So the first criteria is completely fulfilled. When it comes to the second criteria is they must contain delocalization. They must show delocalization, or they must contain delocalized electrons. So there are totally 6 delocalized electrons in the case of furan. Delocalized pi electrons. If you see the structure of furan, as you have seen, so here okay, these two pi electrons, this pair of electrons involved in pi cloud. So totally 6 pi electrons are involved in delocalization. So this is nothing but resonance. This shows the resonance. We can see the resonance structures of a furan when we discuss about the reactivity, when we discuss especially the electrophilic substitution reactions. If it is showing resonance, it definitely gives us a conjugation system. It is a conjugated system. The conjugated system involving 6 pi electrons or 6 electrons. So this again fulfill the second criteria. It shows the resonance, or it involves it can show delocalization of electrons. So third criteria, when it comes to the third criteria, it should obey Huckel's 4n plus 2 pi electron rule. Pi electron rule. So Huckel's rule, what is Huckel's rule? The Huckel's rule is the cyclic planar structure, the completely conjugated system which containing 4n plus 2 pi electrons is aromatic in nature. So here n is the number of rings. If you put n equals to 1, so then 4 into 1 plus 2, that is equals to 6 pi electrons. So you have already seen here 6 pi electrons are there. According to Huckel's rule, the systems containing 2 usually not there, that cyclic, it should not be, it will not be cyclic. Hence 6 pi electrons, 10, 15, 18, these all will show aromaticity. Okay, these all will, it is so on still. These all show the aromaticity. Here we can see in furan 6 pi electrons, as we already seen. So hence it is also obeying the Huckel's rule. That is the third criteria of aromaticity. And when it comes to the fourth one, the compound should undergo electrophilic substitution, because for aromatic compound it is one of the characteristic property, electrophilic substitution reaction. You know, for electrophilic substitution reaction is nothing but the replacement of the proton or hydrogen with an electrophile. So to replace that hydrogen, that compound must contain hydrogen atom. In case of furan, we know its molecular formula, that is C4H4O. There are 4 hydrogen atoms. These 4 hydrogen atoms can be replaced by any electrophile. So hence it also obeys the fourth criteria. Hence when it obeys all the criteria, the first one is cyclic and planar nature, and it should have delocalized electrons, that is showing resonance and with the conjugated system. And third one is it should obey Huckel's 4n plus 2 pi electron rule, and it should have minimum at least one electron for the electrophilic substitution reaction. It obeys all these criteria. Hence furan is aromatic, is aromatic in nature. So this is about the molecular orbital structure of furan, and also we have mentioned its aromaticity. I hope you all understood. So thank you for watching, and please like the video, share with your friends, comment on it, and also subscribe the channel. And please hit the bell icon to get updates of my upcoming videos when they will be uploaded. Thank you. Hi dear students. So now we'll discuss molecular orbital structure of thiophene. You can see sir is already written. No, I'm rewriting, because in the last class we have seen the molecular orbital structure of furan. Both have the same structure, same properties, almost their structural properties. That's why I am just rewriting on the structure. I mean the molecular orbital structure of furan. So I'm taking that and I'm just rewriting. Okay. So if you see the first molecular formula of thiophene is, if I just remove this oxygen and if I write sulfur, this is the molecular formula of sulfur. You know, sulfur and oxygen come under the same group. So oxygen is 8 and sulfur is 16. They both come under the same group and they have the same properties. That's why if I just replace the oxygen with sulfur, that is over, that is done for the thiophene. So if you study furan, we can easily write the molecular orbital structure of thiophene. So that's why I'm just rewriting in this case. So here for the carbon atom, as you already know, the atomic number of carbon is 6 and electronic configuration in ground state is 1s2, 2s2, 2p2, and in the excited state, one of the 2s orbital electron will shift to the 2p orbitals. So here and it is also undergoing same sp2 hybridizations. Here also both carbon and sulfur are sp2 hybridized. So here these three sp2 hybridized orbitals of carbon with the unpaired electron, and there is an unhybridized p orbital, with unpaired electron. For sulfur atom, for sulfur atom, you know, the atomic number of sulfur is 16, and if you write the electronic configuration in ground state, that is 1s2, 2s2, 2p6, 3s2, 12, okay, 3p4, okay, and in the excited state, electronic configuration in excited state, 1s2, 2s2, 2p6. There is no change in this case, because all this 1s and 2s will become 2p. So 1 and 2 principal quantum numbers, they will become inner orbitals. They do not involve in hybridization here. So one of the 3s orbital electron will shift to the 3p orbital. So it is become 3s1, 3p5. In the case of furan, the oxygen was 2s1, 2p5. Here 3s1, 3p5 for sulfur. So these do not involve in hybridizations, inner orbitals. So I am writing for 3s and 3p. Okay, there are 3 orbitals in p orbitals, so that is 3px, 3py, 3pz. Yeah, in case of 3s there is 1 electron. In case of 3p there are 5 electrons. You know, they do not obey Hund's rule. That's why the pairing is not according to the Hund's rule. So here this is also undergoing sp2 hybridization. So 3s, that is 3s orbital and 2 of the 3p orbitals undergoing hybridization, that is sp2 hybridization, and these 3 become 3 sp2 hybrid orbitals. And there is still one unhybridized p orbital, one unhybridized p orbital. As in the case of oxygen, sulfur, both have the same thing. So if I just replace the oxygen by sulfur, sulfur is also sp2 hybridized, and 3 sp2 hybrid orbitals are there, and among 2 sp2 hybrid orbitals with unpaired electron that are forming sigma bonds, and there is one sp2 hybrid orbital with pair of electron that do not involve in a bond formation, that will be present as lone pair over the compound. So, and still it has an unhybridized p orbital with a pair of electron. This is the electronic status of thiophene, sulfur and carbon in the case of thiophene. So now if you see the formation of sigma bond, so if I just replace this oxygen by sulfur, it is over. Here also just oxygen by sulfur, it is over. So please just you can get it. So all carbon-carbon bonds, carbon-carbon sigma bonds are formed by sp2 overlapping, and carbon-sulfur bonds are formed by sp2 overlapping, and each carbon are forming a bond with hydrogen, that is sigma bond. sp2s overlapping leads to the carbon hydrogen sigma bond, and there is a this unhybridized p orbital with lone pair of electrons will be non-bonding pair of electrons that do not involve in the bond formation. So if you see its summary, carbon-carbon sigma bonds and carbon-sulfur sigma bonds, they are formed by the sp2 overlapping, and carbon hydrogen sigma bonds are formed by the sp2s overlapping. There are totally 3 carbon-carbon sigma bonds, and 2 carbon-sulfur sigma bonds, and 4 carbon-hydrogen sigma bonds. This is about the formation of sigma bonds in the case of thiophene. Now we will see the formation of pi bonds in the thiophene. After the sigma bond formation in thiophene, you can see this structure has come. So here the sigma bonds, carbon-carbon sigma bonds, and carbon-hydrogen sigma bonds, and also carbon-sulfur sigma bond. And this is the lone pair of electron or non-bonding pair of electron is present over this. This is the bonding structure of the sigma bonding, it is showing sigma bond. So now I'll take that structure and just rewriting on the furan structure. So for the formation of pi bonds in thiophene, if I just replace oxygen with sulfur as it is we have done in the sigma bond formation. Yes, here also we know that for carbon atom there is one unhybridized p orbital with the unpaired electron, totally for 4 carbons, 4 orbitals, and the sulfur is containing an unhybridized p orbital with a pair of electrons. Okay, the carbon unhybridized p orbital and sulfur unhybridized p orbital, they all will involve in the pi bond formation. They show the sideways or lateral overlapping leading to the formation of pi bonds. So these all are forming a pi cloud over the plane or over and below the plane of the sigma bonds. Okay, so now this is the final structure of thiophene. Indeed, this is also the structure of thiophene. So you can see here, as I have shown the bonding structure pi bonds, I am writing the lone pair inside. So this this pair of electron present in the unhybridized orbital, that is involving in the pi bonding, that is involving the delocalizations of electrons. So here these two and these two, okay, the pi for 2 pi bonding electrons, 2 pi bonding pair of electrons, 4 pi bonding electrons and 1 this pair of electrons. So there is totally 6 delocalizing electrons, and here sulfur. So as I have shown pi cloud which is involving 6 pi electrons, so 6 electrons. So that's why these electrons are involved in the ring. Here I written, so that's why I'm just mentioning only the non-bonding pair of electrons. This is about the structure, that is molecular orbital structure of thiophene. Both furan and thiophene are similar. If you perfectly know the molecular orbital structure of furan, you can easily write the thiophene. That's why most of the time furan has been asked, thiophene still not has been asked many a times. Students, usually the questions will be formed like write the molecular orbital structure of thiophene and mention its aromaticity. So the question will be usually included the aromaticity. Hence now we'll discuss the aromaticity of thiophene. So as you all know, to any compound to show aromaticity, the compound must show or fulfill these 4 criteria that we already discussed in furan. So that's why whether these 4 criteria will be fulfilled by sulfur or not, we'll discuss now. The first criteria, as you know, the compound must be cyclic and involve the planar structure. So as you see here, the thiophene structure, it is completely cyclic. If you start a cycle with sulfur, it will end at the sulfur only. So it is cyclic in nature, and it is planar in nature because the all atoms in the bond forming, that is carbon and sulfur, are sp2 hybridized. As they are sp2 hybridized, the geometry of sp2 hybridized is trigonal planar. So that's why this is a planar in nature. So the first criteria is fulfilled. When it comes to the second criteria, it should have a delocalized electrons. So totally there are 4 pi electrons, 2 pi electron, 2 pi electrons, and these 2 pair of electrons involving the pi bonds, and all these 6 pi electrons will show delocalization, that is forming a resonance structures. We will discuss the resonance structure in detail when we discuss the reactivity of thiophene in the next class, when we discuss especially electrophilic substitution. We have to see the resonance structures of thiophene. This is nothing but conjugation, delocalization of electrons, that is leading to the resonance structure, that is nothing but conjugated system. So here also the thiophene fulfills this criteria. When it comes to the third criteria, so that is the compound should obey the Huckel's 4n plus 2 pi electron rule. The Huckel's rule states that a compound which is cyclic and planar with a completely conjugated system containing 4n plus 2 pi electrons, that will be aromatic. So if I put n here, the one single ring, n equals to 1, so then totally 4 into 1 plus 2, that is 6 pi electrons. 6 pi electrons. So according to Huckel's rule, the system containing 6 pi electrons, 10 pi electrons, 14 pi electrons, 18 pi electrons, etc., etc., they are aromatic in nature. They are aromatic in nature. Here also it has 6 pi electrons. So hence this Huckel's rule also been obeyed by the compound. Hence it fulfills the third criteria also. When it comes to the last and final criteria, that is the compound must undergo electrophilic substitution reaction. For the electrophilic substitution reactions, we need at least one hydrogen, because the hydrogen only will be replaced by the upcoming electrophile. So in case of thiophene, as you see its molecular formula, that is C4H4S, there are 4 hydrogen atoms. These 4 hydrogens can be replaced by an electrophile, so hence it can be undergoing these electrophilic substitution reactions. So all these 4 criteria has been fulfilled by the thiophene structure, hence it is aromatic in nature. Therefore we have to write at the end, the thiophene is aromatic. Is aromatic. Yes, this is about the molecular orbital structure, and also we talked about the aromaticity of the thiophene. I hope you got all these things. Thank you. Thank you for watching my video. Please like and share with your friends and subscribe my channel, and also don't forget to hit the bell icon to get the updates of my upcoming videos. Thank you. Hi students, today we'll discuss about the molecular orbital structure of pyridine. So we already studied the molecular orbital structure of pyrrole, furan, thiophene, and I hope it will be easier to you now to understand the molecular orbital structure of pyridine. So pyridine is the six-membered heterocyclic compound. So this is the structure of pyridine. Okay, and if you write the molecular formula of pyridine, that is C5H5N. C5H5N. As usual, here also both carbon and nitrogens are sp2 hybridized. Both are sp2 hybridized. You all know electron status when they are sp2 hybridized. So for carbon atom, the atomic number is 6 and its electronic configuration in ground state is 1s2, 2s2, 2p2. In the same electronic configuration in its excited state, that is 1s2, 2s, 2p. Here one of the 2s electron will shift to the 2p electron, that is 2s1, 2p3. As usual, inner orbital does not involve in hybridization, so that's why 2s orbital and 3 2p3 orbitals. So this is 2s, these are 2p. You know it is 2px, 2py, 2pz. So each of them are containing an unpaired electron or single electron. Here this 2s, one of the this 2s orbital and two of the 2p orbitals involving in sp2 hybridization. So those will become with equal energy and identical shape. That's why I am writing with condensed structures. So these three are 3 sp2 hybrid orbitals, and each of them are containing unpaired electron, and this 2p z or 2p any one 2p orbital that is also containing unpaired electron, which is unhybridized, which is unhybridized p orbital, p orbital. So for nitrogen atom, the atomic number is 7, the electronic configuration in ground state is 1s2, 2s2, 2p3. The same electronic configuration in excited state is 1s2, 2s1, 2p4. One of the 2s electron will shift to the 2p orbital. So here this also inner orbital does not involve hybridization, and this 2s, 2p, 2px, 2py, 2pz. So here 1, 1, 1, 1. I'm not actually according to Hund's rule, but one of the electron will paired in the hybrid orbital itself. So now this 2s orbital and two of the 2p orbitals, they form hybrid orbitals. These three are 3 sp2 hybrid orbitals, and this is the unhybridized p orbital. So one of the sp2 hybrid orbital is containing pair of electron, and this unhybridized p orbital is containing unpaired electron. Unhybridized p orbital. P orbital. Why this change? Because here you can see carbon are 5. So each carbon is giving one electron. So mean 5 electrons, and this nitrogen is 1. That's why this nitrogen also give 1 electron during the formation of pi bonds. So that will be involving 6 pi electrons. So that forms the most stable sextet form. So that sextet configuration is very much needed to give the stability to the ring, that is pyridine. So that's why one of the sp2 hybrid orbital is paired. Here it is unpaired, unhybridized p orbital. So I'm just summarizing this electron status over here. So for carbon atom, it is sp2 hybridized, and all three sp2 hybrid orbitals are with unpaired electrons. Unpaired electrons, and there is one unhybridized p orbital, one unhybridized p orbital, that is also with unpaired electron, with an unpaired electron. And for nitrogen atom, that is also sp2 hybridized, and here also two of the sp2 hybridized. Okay, two sp2 hybrid orbitals with unpaired electrons, and one sp2 hybrid orbital with pair of electrons. Pair of electron. And there is also one unhybridized p orbital that is also with unpaired electron. So I hope you can see till there, end of the board. Okay, this is the status of the carbon and nitrogen when they are sp2 hybridized in the pyridine. So all three hybrid orbitals of carbon are containing unpaired electron, and one of the three sp2 hybrid orbitals of nitrogen is containing pair of electrons. And this pair will not forming any bond, already it is paired. That's why it will remain as a non-bonding pair of electron that I have represented outside the ring. So now we'll see the molecular orbital structure for formation of sigma bond. Formation of sigma bonds. Formation of sigma bonds. So there are 5 carbon atoms and 1 nitrogen atoms. I'm going to write here. So carbon, 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 and nitrogen. And each of them are sp2 hybridized. So as you already know, sp2 hybridization means the geometry will be trigonal planar with bond angle 120 degree. So one of the carbon with same sp2 hybrid orbitals will overlap with sp2 hybrid orbitals, each of them containing unpaired electrons, and they'll get paired off and forming sp2 sp2 sigma bond, and this overlapping is sp2 sp2 overlapping. Okay, the another remaining orbital sp2 hybrid orbital. So here also the same thing happens with this same carbon. All carbon carbon sigma bonds are formed by sp2 sp2 overlapping. So these all are sp2 sp2 overlapping only. The same way, the one of the hybrid orbital of nitrogen which are containing unpaired electrons, they also will overlap with the sp2 hybrid orbitals of carbon and forming carbon nitrogen bond, sigma bond, that is cn sigma bond. Here the nitrogen here also it is also pairing up with the carbon orbital. So this is also sp2 sp2 overlapping only. And this nitrogen still containing an sp2 hybrid orbital with a pair of electron that do not involve in any kind of bond formation. So hence it is known as non-bonding pair of electrons, or also lone pair of electrons over the nitrogen atom. So this is and still each carbon is containing an hybridized sp2 hybridized orbital with the unpaired electron that is going to form a sigma bond with hydrogen, CH sigma bonds. So the s orbital of the hydrogen overlapping with hydrogen, sorry, sp2 hybrid orbital. So this is sp2 s overlapping forming a CH sigma bond. Same with all the 5 carbons. sp2 s overlapping forming carbon hydrogen sigma bond. Carbon hydrogen sigma bond. So here we can see 3 types of sigma bonds. The one is carbon carbon sigma bond, another one is carbon nitrogen sigma bond, another one is carbon hydrogen sigma bonds. In this carbon nitrogen sigma bonds are formed by sp2 overlapping, and this CH sigma bond is formed by sp2s overlapping. So this is the molecular orbital structure of pyridine for the formation of sigma bonds. And this is actually equivalent to this structure. I'm going to write here. This is equivalent to the structure. There is sigma bond between carbon and carbon. Carbon. This is one of the sigma bond. Here also carbon sigma bond. Carbon nitrogen sigma bond with the pair of electrons, lone pairs. Here is a carbon nitrogen sigma bond, carbon sigma bond, carbon sigma bond. And also each hydrogens are forming sigma bonds with hydrogens, hydrogen, 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 hydrogen. This is the equivalent structure of this one. This is the molecular orbital structure, that is the bonding structure we can show represent here over on the board. So this is the for the formation of sigma bonds. Now we'll discuss for the formation of pi bonds, because we can see here there are 3 pi bonds in the ring. Yes, formation of pi bonds. As you all know, the pi bond is formed always after the formation of sigma bonds. So that's why I'll take this structure, the structure after this formation of sigma bond. So carbon, nitrogen, carbon, and the nitrogen is still with the hybrid orbital with pair of electrons. We can represent with the dots or that arrows. Okay. So here, after the formation of sigma bonds, each carbon and nitrogen still have an unhybridized p orbital, that is present perpendicular to the plane of the sigma bond. Yes, and each of them are containing with an unpaired single electron. So I'm just writing opposite spins, because when they are only opposite spins, then only they will get paired up. So these all p orbitals, unhybridized p orbitals with the unpaired electrons will show sideways overlapping or lateral overlapping, that is going to form pi cloud or pi bonds in the pyridine. So always you know the head to head overlapping or axial overlapping forming sigma bonds, and here the sideways are lateral overlapping. This upper lobe, same upper lobe forming a pi cloud over the sigma bond. The same way the lower lobe will show a sideways or lateral overlapping, that is forming a pi cloud. So there are totally, this is the final molecular orbital structure of pyridine. So here you can see each carbon will give one electron and also nitrogen will give one electron. So totally here we can see 6 electrons in the pi bond formation. So 6 pi electrons, and all these 6 pi electrons are delocalizing electrons. So that is also giving the aromatic property to this compound. This structure is now equivalent to this structure. This one, or the same like this, or yes, okay, and still there is one lone pair of electrons on nitrogen. This is about the molecular structure of pyridine. Students, usually the questions are framed like write the molecular structure of pyridine and mention its aromaticity. Usually the aromaticity is also been asked along with the pyridine. So as we already seen aromaticity for all other compounds, that is pyrrole, furan, and also thiophene. So let us discuss that thing also here. So you already know that 4 criteria should be fulfilled by any compound to show the aromaticity. The first criteria is that the compound should be cyclic and planar. You know this pyridine is also cyclic and planar. So if the start ring with nitrogen, it ends up with nitrogen. So it's a cyclic, and also as it is sp2 hybridized, it shows the trigonal planar geometry, hence it is planar. So hence the first criteria is fulfilled. The second criteria is it should have a delocalization. It should show delocalization of pi electron. Delocalization. So here we have just seen that 6 pi electrons. So that is a sextet. All sextet pi sextet is always a strong or giving a strength or stability to the compound. So 6 pi electrons are involving in delocalization. So it shows resonance. It's a completely conjugated system that we can see also resonance structures of this pyridine when we discuss the reactivity, especially the electrophilic substitution reactions of pyridine in the next class. So this is also fulfilled by the pyridine. The third one is it should obey Huckel's 4n plus 2 pi electron rule. As you already know, there are 6 pi electrons and one ring, so n equals to 1. So 4 into 1 plus 2, that is equals to 6 pi electrons. So you all know any compound which is cyclic and planar and showing completely conjugated system with 6 pi electrons or 10 pi electrons, 14 pi electrons, 18 pi electrons could be aromatic. So here it is showing a 6 pi electrons, hence it is also aromatic and obeys the Huckel's rule. Hence it fulfills the third criteria. When it comes to the fourth criteria, that it should undergo electrophilic substitution reaction. The compound should undergo electrophilic substitution reaction. As you all know, for electrophilic substitution reaction, there must be at least one hydrogen atom to replace. So here also we have 5 hydrogen atoms. So those 5 hydrogen atoms can be replaced by any other electrophile. So hence it may show electrophilic substitution reaction. Yes, but there is one problem in this compound. It is not much easily undergoing electrophilic substitutions. So there are two other reasons. So that is also been asked in exams, why pyridine does not undergo electrophilic substitution easily. But pyrrole, furan, thiophene are easily undergoing electrophilic substitution reactions. But this pyridine is having difficulty in undergoing electrophilic substitution reactions. Let us see that. The one reason is that, if I give the reason, yes, here you can see the structure. Nitrogen. So this pi cloud is nitrogen is, as it is more electronegative element which can attract this pi electron towards it, which can attract pi electron towards it. So hence there is a partial positivity may occurs on each carbon. There is a partial positivity may occur on each carbon. So when there is a positivity, so the hydrogen cannot be removed because hydrogen is also positive. Understanding? So hydrogen cannot be easily removed. Already they are showing positivity. So if it is able to remove that hydrogen, that compound will become unstable. So as the nitrogen atom is more electronegative, hence this compound will always repulsive when it undergoes electrophilic substitution. So it cannot easily give that hydrogen electrons. Okay. And the second reason is also one more reason. First reason, as this lone pair is there, it is more active. It is more active. It is actually here when an electrophile is introduced. So this electrophile, instead of replacing these hydrogens, instead of replacing the hydrogens at the carbon, it will attack on the nitrogen atom. It will attack on the nitrogen because it is having negativity, because lone pair of electrons are over there in the nitrogen. So hence it is going to form this compound. Hydrogen, sorry, electrophile with the positive charge. So this is going to form an ion. So this ion is pyridinium ion. Pyridinium ion. This pyridinium ion, as it is a positive charge, it shows resonance also, hence it is become also stable. So hence here this electrophile, instead of replacing the hydrogen, it will be attacking the nitrogen atom. Hence these two reasons are actually making this pyridine to not undergoing these electrophilic substitution reactions. But at vigorous conditions like high temperature, high pressure, this pyridine also can undergo ionization reactions. Hence it is also considered as aromatic. It is also considered as aromatic. Pyridine is also one of the aromatic compound. But these are to the two reasons which is definitely and usually most commonly asked in your exams. Why pyridine does not undergo electrophilic substitution reaction? The first reason is the pyridine is more electronegative element which pulls all the electrons, pi electrons towards itself, and it is making the hydrogens to remove from the compound is difficult. And the second reason, when the electrophile is introduced, electrophile directly attacks the nitrogen because it is carrying a lone pair of electrons. So yes, not like this here. Yeah, the arrow mark should be towards the positive charge. Okay. So these two reasons make pyridine less active or less reactive towards electrophilic substitution reaction. This is about the aromaticity. but pyridine is also completely aromatic, though it has some difficulties in the electrophilic substitution reactions. Thank you for watching, and as usual, please like the video and subscribe to my channel and hit the bell icon to get the next updates by me. Thank you.